On your hit list, and you're going to keep me honest. The pinna or the auricle, that's this part of your external ear right there. The external ear, your auricle, your pinna, auricle or pinna. Then going through here, this is where sound waves enter. I'm going to turn this so we can see. We're going through your external auditory meatus. You oftentimes stick things into your external auditory meatus that you probably should not, right? Okay, so that's the external auditory meatus. What travels through there? Sound waves. As we go through the external auditory meatus, we hit this structure that I'm going to take out of the model so you can see. That structure there, that film structure is called the tympanum, also known as the tympanic membrane. The purpose of the tympanum, and this is all also talked about in the video, for your lecture video, the tympanum vibrates. As the sound waves hit it, it vibrates back and forth. Now, there are 3 ossicles, and we learned about the ossicles in our bone unit. The 3 ossicles in order are the malleus, the incus, and then the stapes. We do not call them the hammer, the anvil, and the stirrup. That is not what we call them. So right here we have the malleus, and then we have the incus, and then over here in this model, because this is where we have it, is the stapes. And I'll show you over here. I'm trying to adjust this. The stapes, it looks like a stirrup. That's its name. That's what it's named for. And the purpose of those auditory ossicles is when the tympanum starts to vibrate, those ossicles start to move. And they're all anchored to each other. And eventually, the stapes starts to pound on the oval window. The oval window is not on your hit list, but when you watch the lecture on the ear, you will learn what happens in the oval window. So I'm going to default to lecture on that. Going back to our model, there's another structure here, right here, and this is called the Eustachian Tube. I'm going to hold it up so everyone can see. That's the Eustachian Tube. There's another name for it, Auditory Tube. Auditory Tube, and there's another name for it, Pharyngotympanic Tube. So there are multiple names for that. This is the auditory tube. You need to be careful because the auditory tube is different than the auditory canal. The external auditory meatus leads to this long canal called the auditory canal. And those two things sound very similar. Auditory canal, auditory tube. I think you should call it pharyngotympanic tube because that word, pharyngotympanic tube, tells you that this is a tube that leads to your tympanum and also to the back of your throat, which is the reason why when you actually are going up to altitude on a plane, let's say, and you can't hear well and your ears feel plugged, you yawn. And when you yawn, you introduce air through this pharyngotympanic tube, and that allows your tympanum to now bend and flex with the sound waves. So you're not talking like you're on a mountain. Right? That's good. Now we're going to go to the inner ear. The inner ear, we have, this is the inner ear here. And we have soft membranous structures that are protected by bony structures. And in my lecture, you'll hear me say it's a lot like if you're looking at an aquarium. And the aquarium is a hard structure, right? It's made of glass, and inside there's fluid. And inside, swimming around in that fluid, we have soft structures that we call fish. And inside them, there's fluid, blood, right? We're going to see 3 different places in the inner ear where there's a bony container, then there's fluid in it called perilymph, then within it are soft membranous structures, and within them they have fluid called endolymph. So think aquarium, water, fish, blood, okay? So the first bony container is this structure here. That's called the vestibule, right there. The vestibule. And there are 2 soft membranous structures. This is the vestibule, what I'm holding between my fingers. That's the vestibule. And inside are soft structures called the utricle and saccule. All 3 of these pieces of the inner ear I'm going to address, they have modified hair cells, modified neurons. And in your lecture exam and on your quiz when you get back from spring break, I'm going to ask you how these hair cells register placement of you in the body, like where you are in space, or how they register sound. And you got to get these hair cells to bend. And each of these 3 bony areas with their soft structures have a unique way to get the hair cells to bend to start an action potential. The utricle and saccule are going to have structures, calcium carbonate, crystals called otoliths. And the utricle and saccule, they send information to your brain about where your head is. Is it like this on the side? Is it forward? And it also gives information about how fast you're accelerating in a linear fashion. I tease my honey. I don't even have to look at the speedometer. My utricle and saccule alert me when he's speeding. I have an overactive utricle and saccule. And these otoliths, depending on how fast you're going or how your head is tilted, they're like sand crystals. And as they fall from the gravity, they press on the hair cells, and that sends information to your brain where it interprets where you are, where your head is placed at any given moment. Now we're going to move on to another bony structure and another soft membranous structure. The bony structure shown here, these circular things, they're half circles, they're called semicircular canals. That's the bony part. The soft membranous structure is shown here with this clear tube. That would be the semicircular canal. They too have these hair cells, and they have to use a different mechanism to get them to bend. You have 3 semicircular canals. You have an anterior, you have a posterior, and you have a lateral. When the hair cells bend, the hair cells send information, action potentials to your brain, and your brain will interpret how you're spinning. Are you spinning? Now, weird thing is, those otoliths that I told you about in the utricle and saccule, they can actually get loose. They can accidentally show up in those semicircular canals and trigger the hair cells. And then people get the sensation that they're spinning when they're really not. That's vertigo, right? And they can get those otoliths going back to where they should be. You have to go see a doctor, and they'll do a series of tilting your head trying to get the otoliths back to where they're supposed to be. It's a lot like, do you ever see those Cracker Jack games where you have the little metal ball and you have to try and get them in the little hole? It's sort of like that, and you're like, trying to get it. They'll do that with your head, trying to get those otoliths back into the utricle and saccule. So in these semicircular canals, the hair cells have a gel over them. So we're not using these sand crystals, but we're using a gel. And this gel cap is called the crista ampullaris. And the gel cap itself is called the cupula. And as you're spinning, this gel cap, the cupula, bends the hair cells inside the crista ampullaris. And again, you'll learn about this in lecture, and you'll see pictures of it. It's not here on the model. And your brain will interpret that as, how are you spinning? If you are ever unfortunate enough to be trapped in an avalanche, people do survive them, and they tumble all the way down the mountain. Their crista ampullaris, their hair cells are overstimulated, and their brain is getting all this information. And when the avalanche stops and they're trapped in the snow, their brain is so overloaded they don't know which way is up or down. And they start trying to dig out, and they're actually going deeper, not towards the surface. And they're running out of air. You don't have to be in an avalanche. Perhaps you swim in the ocean. Have you ever gotten tagged by a ruthless wave, pulls you under, and you feel like you're in a washing machine, and there's sand all around you? It's very difficult to figure out which way is up and which way you're going deeper into the ocean. You need to be calm. If you're underwater, all you have to do is blow bubbles and follow them, right? If you're in an avalanche and you're trapped in snow, you just got to dig a little and see which way the snow is falling, right? Then you know which way is towards the ground. Or spit. Follow your spit. Do something, but don't just start digging and swimming until you take a pause and do something logical to find which way is up and which way gravity is going. Yeah. But we don't think about these things when we're scared, right? So the next part I want to point out is the cochlea. And the cochlea is named that because it looks like a snail shell. That's the cochlea. And inside the cochlea is, again, a soft membranous structure called the cochlear duct. And again, we're going to see hair cells. And these hair cells are part of what's called the spiral organ. That's what we're supposed to call it. In your lecture, you'll hear me call it the organ of Corti. And the sound waves that were coming through your auditory canal eventually get to that spiral organ, and the sound waves get transferred into pressure waves of liquid. And as the spiral organ is undulating back and forth, it bends the hair cells on a membrane. And I'm going to pull out another model and show you this. And that will send action potentials through this cranial nerve called cranial nerve 8. And it's called the vestibular cochlear nerve. So that vestibular cochlear nerve is a sensory nerve sending action potentials to your brain, and your brain can then interpret the placement of your head. Are you spinning? And what are you hearing? Did I miss anything on your hit list?
No, you're good.
We're good?
Mm-hmm.
Then we're done.